Hello everyone, I'm Mrs. Amel Hadj, a teacher of physics at Oran2 University. In this presentation, we will explore together a fundamental topic in classical mechanics, the kinematics of material points, the study of how objects move. And we will focus on the material point, which is an object of masses m considered as dimensionless particle. Object of kinematic. Kinematics is concerned with the measurement of the state of motion of material points, position, velocity or speed, and acceleration with respect to a frame of reference, without attaching to the causes that produce this movement and the forces acting on it. These physical quantities are vector quantities, meaning they have not only magnitude but also a direction and a point of application. To determine this component, it's necessary to choose a coordinate system. Reference. The choice of reference frame often depends on the physical problem to be solved and the simplifications we wish to bring to the study. Let's start by discovering the main reference frame. Three coordinate systems are commonly used to describe the position and movement of material points: Cartesian, cylindrical, and spherical coordinates. Cartesian coordinates utilize three perpendicular axes x, y, and z. This system is practical for mechanical systems such as the movement of a particle along a plane. Cylindrical coordinates. A point P is specified by r, phi, and z, where phi is measured from the x-axis. Useful for problems with cylindrical symmetry, such as fluid flow in pipe or magnetic field of a string conductor. Spherical coordinates use a radical distance and two angles to describe the position of a point in the space with spherical symmetry. So, P is specified by r, theta, and phi. R is measured from the origin. Theta is measured from the z-axis, and phi is measured from the x-axis. Ideal for problems with spherical symmetry such as gravitational and electrostatic fields around spherical body. The position vectors is fundamental in describing the location of points, helping in analyzing the motion and position of a particle and object in space. Cartesian coordinates. The position m of a point in space is represented by vector OM originating from the origin of the coordinate system to the point in question. This is done by projecting the point onto the three plane. So, we define a Cartesian base and we write position vector. Cylindrical coordinates. The position of a point M is described using a radical distance from a chosen reference axis, an angular coordinate around this axis, and a height along this axis. So we define mu cylindrical base, UR, U theta, and K, This base is a local base. That means it varies with the variation of a position of the points M, and the position vector in cylindrical coordinates is thus represented differently than in Cartesian coordinates, is written like this. Spherical coordinates, the position of a point M is described using three parameters: the radical distance from chosen reference points, usually the origin, the polar angle from the reference axis, usually the z-axis, and the azimuthal angle from a reference direction in the reference plane. So we define a new spherical base UR, U theta, U phi. Same thing, this base is local base. In this coordinate, the position vector is written like this. To continue studying our motion, we need to find the velocity vector and acceleration vector. Let's begin by the average speed. The average speed, Vm, gives us only a rough idea of the movements. To know the speed of mobile at a time given, we then define the instant speed, which is obtained when the time interval delta t tends towards zero, like this formula. The instant speed vector is tangent to trajectory. Its sense is the same of movements. Average acceleration vector of the material points M between two moments T1 and T2 corresponding to the M1 and M2 position is defined by the vector AM, such as the instant acceleration vector of the material points allow us to know the acceleration of these points at a given time. It's obtained by reducing the time interval delta t to zero. We recognize the expression of derivative and we note Let's begin by Cartesian coordinates. When the material points M move an infinitesimal amount in space, that means an elementary displacement of the position M to a very close position M prime. The elementary displacement vector is given by So, the components of the velocity are calculated by the first derivative of the position vector with respect to time. How about acceleration? The components of the acceleration vector are calculated by the first derivative of a velocity vector or the second derivative of the position vector with respect to time. Cylindrical coordinates. An elementary displacement of the position M with coordinate r theta z to a very close position M prime with components r plus dr, theta plus d theta, and z plus dz is shown in the figure, where dr represents movement in direction of ur, and arc of length r d theta tangent to u theta, as well as the displacement dz in direction of k. So, the elementary displacement vector is given by, and speed vector, first derivative with respect to time. Acceleration vector, finally, spherical coordinates, the elementary displacement of the position m r theta phi to a very close position m prime r plus dr theta plus d theta phi plus d phi is shown in the figure, where dr represent movement in the direction of ur, an arc of length r d theta tangent to u theta, and r sinus theta d phi in direction of u phi. The same thing, speed vector, first derivative of position vectors. Position vector is given by this formula. Thank you for your attention.